Welcome to General Chemistry Mini Lecture Series, Lecture 57, Real Gases. This is the last lecture of this General Chemistry Mini Lecture Series. In this slide, we are going to concentrate on the effects of size and intermolecular forces. As we already know, ideal gas law only applies to monoatomic gases at high temperature and low pressure. But in reality, real gases normally don't behave like the ideal gases. For ideal gases, we assume that there are no attractions between gas particles. Also, gas particles, they don't have volume, remember? We assume them do not have volume. That's why they don't take up space. However, at low temperatures and high pressures, those assumptions are not valid anymore. And you can take a look at the molar volume of different gases. Ideal gas. For ideal gases, doesn't matter what the identity of the gas is at standard temperature and pressure conditions. 1 mole of any gas should contain 22.41 liters. However, if you look at those different gases, so chlorine is 22.06 liters, the molar volume. CO2, 22.31, and they all deviate from the molar volume of ideal gases. The smaller gases, on the other hand, they don't deviate that much. You see hydrogen, H2, hydrogen gas, H2, 22.42 versus 22.41 for ideal gas. Helium, exactly 22.41, the same as ideal gas. So the difference is really the size. Chlorine, CO2, they are much larger molecules, so the size is much larger. Therefore, actually, it's deviated more from the molar volume of the ideal gases. And those smaller gases, the smaller size, the gases with a smaller size, they don't deviate that much from the ideal gas molar volume. Yeah, let's take a closer look at the effect of molar volume. At high pressure, the amount of space occupied by the gas particles is a significant amount of the total volume. So at high pressure, which means the volume matters. Therefore, the molecular volume makes the actual volume larger than the ideal gas law would predict. In order to compensate that deviation, van der Waals modified the ideal gas law equation. Volume from the ideal gas law, PV equals nRT, we can write V equals nRT over P, but he added one more term, NB. So B is called the van der Waals constant, and that constant is different for every gas because their particles have different sizes. Now the effect of intermolecular interactions or the attractions among the gas particles. At low temperature, the attractions between gas particles is very high actually, so cannot be ignored. Then the intermolecular attractions makes the real pressure less than the ideal gas law would predict. So therefore, the modified equation for pressure of real gas contains a term of A times N over V squared. And A is called the van der Waals constant, And again, it is different for every gas due to the different sizes. Now let's take a look at the whole van der Waals equation. You see, the ideal gas law, the equation is PV equals nRT. Now the PV part after van der Waals modification becomes this, right here. And then PV equals nRT. So therefore, the van der Waals equation is changed from PV equals nRT to P plus A, then N over V squared times V minus NB equals nRT. And this van der Waals equation is used for real gases. Again, A and B are called the van der Waals constants, and they are different for each gas. Here is a list of those van der Waals constants of A and B. The gas with a smaller size, actually those constants are rather small. So therefore, the deviation of the real gas from the ideal gas is smaller. Well, the heavier ones you see right here, like for CO2, is 3.59, and for CCl4, 20.4 for the A constant. That's very, very high than the helium 0.03, which means those heavier gases, they deviate much, much more from the ideal gas. Again, from the real gas law, PV equals nRT, we can write down N equals PV over RT. And if N equals 1, which means PV over RT equals 1, all right? And this y-axis is PV over RT, therefore 1 for ideal gas, that stays the same, regardless what the pressure is. And then the real gases, they don't follow this ratio of 1. You see, when the pressure increases, helium, that ratio PV over RT, which is n number of moles, actually changes. And as a matter of fact, it increases. And then for some other gases, also water vapor, first decreases and then increases. For cyanide, you see, increases. So there's a difference between real gases and the ideal gas. So the curve I just mentioned a while ago, for a real gas, the PV over RT ratio is generally lower than the ideal gas at low pressure. You see, that actually means the most important factor is the intermolecular attractions. And then the fact that this PV over RT ratio for most of real gases, they are normally higher than the ideal gas at higher pressure. And that means the most important factor in this region is the molecular volume. In short, at the low pressure region, the important factor affecting the PV over RT ratio is the intermolecular attractions. And at a higher pressure, the most important factor is the molecular volume. That's it for lecture 57. And as a matter of fact, this is the last lecture of this general chemistry mini lecture series. I hope this series help you learn chemistry, and I wish you all a very bright future and happy studying chemistry. So long.